So exponential decay. So decay or decline of a population is represented by PT, where we have P sub 0 e to the negative KT. So we have make sure for decay that our rate is going to be negative. And in this case, half-life is going to be the amount of time it takes for my substance to decay by a half of its original amount. So when we talk about decay, we don't care about doubling times, we care about half-life. So this doesn't always just apply to populations, this applies like things like elemental decay. Someone said electron decay. Elemental decay, you know, like carbon-14 or something like that. That is something that also follows this exponential decay. So just to show you, this is what the growth looks like, and this is what the decay looks like. So as you see, what really happens is that this is just a reflection over the y-axis. So for first example, like I said, it's not always about population. Adults can safely lose about 2% of their weight a month with diet and exercise. So it's a safe amount. So my K that I'm looking at is going to be 0.02. With an individual, if an individual has a weight of 110 pounds, their initial weight, and tries to lose 2% each month, how much should they weigh? Wow, this is the wrong way. How much should they weigh in a year? So PT equals P naught e to the negative KT. We know the initial weight is 110 pounds, e to the negative 0.02, because now we have decay. So T, we want to figure out how much they lose in a year, and we were talking about the rate in months. So T should actually be 12 months. So if you look for P of 12 is going to be is going to be 210 e to the negative 0.02 times 12. Okay. I was actually a little surprised by this when I calculated it earlier. I was not expecting 2% to add up so much, especially when we have decay. But according to our calculations, what we should have is that this person should weigh about 165 pounds. I'll say 65.2 pounds. All right, so keep going on with this. The decay rate K and the half-life T are also related. There's something very similar. Except your book made a mistake, and this should all be 1/2. So KT equals the natural log of 1/2, or K is the natural log of 1/2 over T, or T is the natural log of 1/2 over K. So note that the relationship between decay rate and half-life is the same as between growth rate and doubling time. Oops, yes. Okay. So just bring this up, actually, this would be appropriate because I forgot we are going to get a positive K, and then we're going to turn it negative. So if you had originally did not have this formula set up as your K's are always have to stay positive, then you would use a natural log of 1/2. So all that's going to do is just change it from a positive to a negative. But just remember, that when you're doing a decay, that K, when you put it in the formula, has to be negative. All right, so for carbon dating, the radioactive element carbon-14 has a half-life of 5,750 years approximately. The percentage of carbon-14 present in the remains of organic matter can be used to determine the age of the organic matter. Archaeologists discovered that the linen wrappings of one of the Dead Sea Scrolls lost 22.3% of its carbon-14 at the time it was found. How old was the linen wrapping? So they would know by looking at linen wrappings created now how much carbon-14 should be in it. That's how they know how much it's lost, just to put that out there. So we can tell how much it's lost, and where you can use the ideas of elemental decay and half-lives to figure out how old this stuff is. So take a minute and see if you can work this out, and we'll do this together. All right, so this is going to be a multi-step problem. The first issue that we have is that we really don't know what our decay rate is. And so that is sort of an initial issue that we have. We have the half-life though. We know what is K. So we know that K times T equals natural log of 2. So like I said, we can still use this formula. It's going to be fine. We know that T is 5,750 because that is the half-life of carbon-14. So if I want to know what K is just natural log of 2 divided by 5,750. So K is going to be approximately, keep accidentally erasing this, divided by 5,750. All right. So make sure when you divide by the 5,750, you do not keep it in the logarithm. I accidentally did that. But this comes out to, you might see something like 1.205 x times 10 to the negative 4. That just means that I just have to move my decimal place to the left negative 4. So if I do that, that is going to be 1231204. The decay rate is 0.0001205. Okay, so what my formula is going to be for the decay rate for carbon is P to the T, P sub naught, we just need to know what P sub naught is, E to the 0.0001205 T. So the next part of this is just figuring out what we have for PT and P sub 0. So remember, we lost 22.3%. So if you want to, you can kind of pick some arbitrary, and it's usually easy to pick like 100. Let's say P sub 0 was 100. There was 100 carbon-14s, I guess, inside. That means if this was true and we lost 22.3%, then P to the T has to be what's left over. And what would be left over would be, make sure I had that right. Yeah, would be 77.7% is left over. So that's what we lost, but this is what we should have. So if I had a 100 carbon-14, then what should be left is 77.7. So if we want to figure out how old that wrapping is, we have a good percent of our information, pretty much everything we need to figure that out. So we're going to say P sub t is 77.7. We're going to say P sub naught is 100. And then we have e to the 0.0001205 t. So what we're going to have to do is we're just going to have to solve for t. So if I divide both sides by 100, I'm just left with 0.777 equals e to the 0.0001205 t. If I do a natural log of both sides, I'm going to be left with a natural log of 0.777 equals 0.0001205 t. So if I want my t, that's just going to be natural log of 0.777. Oh, one mistake here. Because we have a decay rate, that should be a negative out front. Make sure all of these are negative. So we're dividing by negative 0.0001205. So natural log of 0.777 divided by a negative 0.0001205 is going to give me 2,093 let's say 9 years old. So we'll just round this even more. Let's say this is 2,094 years old. So just to point out, if I had made a mistake and I forgot that negative, I would have ended up with a negative year, just to point that out. So that's what we need the negative for, is to make sure that when I do this and I get my years are positive years, something makes sense. All right. So according to carbon dating, if we were carbon dating of these Dead Sea Scrolls, we would have to say that they're 2,094 years old. So that is going to be the end of your college algebra. I hope this was fun for you. And I hope that you did learn a lot. So just remember that the whole next week is really just studying for those final exams and finishing those final exams. Like I said, I hope you had a great time and I hope you got a great grade. See ya.